It'll be a short class. Thanks for coming. So we're just going to wrap up, and I thought I'd take this opportunity. We're going to talk a little bit more about that earthquake, the big one in Japan, just because it's so interesting. I just want to mention that Wednesday is the review for the final, so if you're going to take the final, be sure to come then. Scheduling issues, as far as the final exam goes, some folks have been asking. Study guide should be asked. 1 to 3 are still posted and relevant. Didn't put on my microphone. So go ahead and if you need to re-download them, go ahead and do that. And if not, just make sure you go over them again if you take this final. Again, the final's optional. We'll go talk about that a little bit more on Wednesday if you're planning to take it. Office hours Tuesday, Wednesday, and Friday, 10 to 11. Or if you can't make any of those times, by appointment sometime on Thursday. Okay? And if you can't make any of those times, I might be able to fit you in some other time, but let's try to fit into that. And of course, your TAs will have office hours as well. Okay, just real quick. So this is, I won't stress you out too much about it, but I just think this is really interesting. I don't think we're really on the final or anything here. So what I want to talk about a little about is this plot. And what this plot is of earthquakes, okay? And this is the typical number of earthquakes per year worldwide, okay? And so first let's just focus on that sort of brownish area. And you can see that, what do we have on the left side? We have magnitude. And remember that magnitude is logarithmic. So even though we don't have tens, tens are 10 times greater than 9s and 10 times greater than 8s and so forth. But what you'll see is that down here by 2, we have this number of about 1 million. So magnitude 2 earthquakes and below, we have about 1 million of those a year. It's quite a lot. And it turns out that as you go up, you get progressively fewer and fewer logarithmically. Okay, not surprisingly, that's why we use that logarithmic scale. But the other part of that is, on this side is the total amount of energy. And this is an equivalence of pounds of explosive. So I don't know if it's a multiple of 1,000. No, it's just that pound. So a 2 is 120 pounds of explosives. A 3 would be 4,000, so roughly 30 times more or 30 times larger than a 2. And then we go up. You see how they jump back and forth, 30 times as large. Now, we've had some really big earthquakes recently. Starting in, let's say, 2004, we had the Sumatra earthquake, and that one sort of fit up here. And that, they have it as, I guess, about a 9.3 or so. And that's roughly where this Japanese, the Honshu earthquake fit in, somewhere in there. So, and again, another enormous earthquake. The other thing you want to keep in mind, I put these 2 yellow lines here, okay? So let's just say our Japanese earthquake was about a 9. Then we looked down. We had some really big earthquakes. 4 shocks came before the big earthquake, and aftershocks came after the big earthquake that were in the order of magnitude 7 and greater. And under normal circumstances, that would be a huge earthquake, turns out. 7s can be pretty damaging depending on where they go and how deep they are. Turns out, again, when we think about it, how much energy is in a 7 compared to a 9? Turns out, if you look at it, they're about you'd have to have 1,000 magnitude 7 in themselves, pretty large earthquakes, very large earthquakes, again, depending on where they are, to give you the energy of 1 magnitude 9. So I'll show you a couple movies in a second, and what I want you to take from it is that even though we had this big earthquake beforehand, we didn't release very much energy relative to how much energy. Just trying to visualize how much energy is in that earthquake is difficult, the 9. But I'll try to show you this movie real quick. Actually, let's go to the next slide. We'll come back to this. Let me see if I can open these movies up. I should have done this before. Okay, so here, the next couple movies I'll show you are just the earthquake epicenters, and then I'll show you the focus, meaning the 3D location of these earthquakes. It's pretty cool. So what do we have here? Here's a topographic map, a contour map of the Japanese island, North Island of Japan. And so you can see here, this is the actual part above sea level, right? So this is the volcanic arc, that's the Japanese islands. And here we can see additional lines in blue, and this is going down to the trench. The trench would be somewhere here. So you'll see some dots. And this one is starting in 1973, okay? And what I want you to see is when we get to this recent earthquake, how much larger this earthquake was compared to the historical seismicity from we're only about, what, 35 years. Let's see if we can get that. Okay, here we go. So each one of these is a small to large earthquake, right? And they're disappearing, otherwise this plot would get really busy. But you can see the time up here, 1980, 1981, 2. So it's pretty rapid, and you saw a big earthquake back there and some aftershocks. And then here's another sort of large earthquake. And now we're in 1990, here is another earthquake here. But again, you can see some places are repeating earthquakes. There's a big one up there and a lot of aftershocks after it. But wait till we get just a little bit further and we'll see that last one we just had. Just in terms of the number of aftershocks, while they don't tell you how much energy is being released, they certainly give you a sense of the effect and magnitude just based on the number of events. So here we are, 2010, 2011. Okay, so you can see that just in that one event, right, we've got a huge number of earthquakes plus aftershocks. Okay, so next movie. The next movie is, let me show you this one. Takes a second to load up. So here's that just localized to the time frame of that event. And what I'll tell you is really cool about this event is that in most cases, when you have a magnitude 7 event, that's considered a major event, okay? And people stop and take a look and be thoughtful about that event. And then it turns out that we had a foreshock. So you typically don't have a foreshock that's so big. But then we had a magnitude 9 where you can sort of see it right in there. But let's look at this movie. And this might go too fast, but I'll play it again if it goes fast. So here's the foreshock, right? So you can see the day, and then we had the big event, and then all these are aftershocks after it. And they're continuing on till today, so there's still been a number of 5s and presumably lots of smaller earthquakes that don't get reported widely, but these are all fairly large earthquakes in here. And you can see they just keep going on and on. And so now we're at 4/2, what's today's date, the 25th. So I think this only goes up to the 7th. Yeah, and that's the last large. That was, I think, something on the order of a 6 or a 7 in there. So you can see that from the historical record, which is not that long, what I said, 35 years, there's a lot of seismicity in this area. This is a convergent margin. You have a lot of earthquakes, and as a result, you have a lot of activity and aftershocks and foreshocks. But just the degree to which this one earthquake just overwhelms everything, it's just sort of changed the whole, as far as seismologists are concerned, it's changed the whole game in terms of trying to understand what's going on here seismically, because it sort of overwhelms the signal from all those other earthquakes. Okay, we'll just watch this one more time. But you can see why do we have aftershocks and foreshocks? So let me tell you a little bit about that. So when we have a small earthquake, okay, a fault ruptures, and remember we have that elastic component. This part you might want to, if you're going to take the final, that'd be relevant. You have that elastic component, it builds up, and then you have slip on the fault, and that's your earthquake. And that earthquake releases energy. Sometimes, though, when you have very large earthquakes, you have to rupture a much larger piece of fault, okay? And so as a result, parts of the fault rupture will go too far, some won't go far enough, and as a result, that fault system has to readjust. And it readjusts by having smaller earthquakes along the fault to make up for any deficit or excess in motion. And so frequently, like we've seen here, you have a really big earthquake, and then you have these smaller earthquakes for a very long period afterwards. Okay, one more thing. We all know about GPS, right? We have it in our phones, we have it in our cars, we have it all over the place. But the way geologists or geodesists use GPS is a little bit different. They don't just try to figure out where they are and where they're going. They'll take their GPS and put it out somewhere, and they'll keep it out there for a really long time. And what they're trying to figure out, not just where they are, they can easily determine that, but how fast the Earth is moving underneath them. And they're not looking for within a meter, they're looking within a millimeter or so. That's the sort of error that they want. So here again we have the Japanese islands, and it turns out that Japan, because it's been so seismically active through its history, is one of the most instrumented places in the world. And almost every inch of this island is either got a seismometer or a GPS unit on it, okay? And so this movie, this animation, is going to show you the horizontal component of displacement and the vertical displacement, okay? And so as these arrows get larger, that means the Earth is going up. These will actually show you the direction of horizontal motion of what's going on. But as the earthquake comes through here, you can actually see these individual GPS units moving around. So we'll take a look at this movie because it's awfully cool. This is real time, mind you, so this was actually recorded data. Okay, so this is, so far in the beginning, this is background noise. You can see not much motion. There's a little bit of, the plates moving. There was the earthquake. And then all of a sudden that earthquake has to propagate in. And all of a sudden the ground surface is moving, right? Because this was a thrust earthquake. This is being thrust over the downgoing plate. And you can see that motion. The Earth is moving, cascading motion all the way back. Okay, and this is in seconds, just so you know. This is how quickly the Earth can move. And look at how the Earth is moving up. It's moved up considerably. Oops, there's a little glitch in there, but you can see that that's showing you the total motion that those receivers underwent. So that patch of ground underneath that. So again, when you have a fault, a rupture, when you have an earthquake, the Earth is moved, and it's that motion that's sending out those seismic waves, and we can record it in real time if you have enough GPS receivers. Okay, so finally, I'll just show you one more thing. Actually, in the Internet Explorer. And this is a 3D animation of sort of what I've been showing you. I don't know how well it's going to turn out. But you can see that we've been looking at everything in map view. And obviously, these earthquakes that happen don't happen just simply in map view. They happen at different depths. So every one of those earthquakes happened at a slightly different depth. But they all define sort of a fault rupture. And so when one part of the Earth, especially when you've got that, now that's just the location and sort of the error associated with that initiation. But remember, the fault will rupture widely past that. That's where it started. And then all these aftershocks define the total rupture area. So this is a huge swath of Earth that has moved. So yeah, and the magnitudes were from 4 to, well, obviously that was a 9, so it's, I guess the aftershocks are 4 to 7.9. So again, just another way to visualize what we've been sort of talking about and how the sort of the relevant part of earthquakes for you guys. Okay, so thanks for indulging me on that. I think it's really important, relevant, and timely to sort of maybe go back over that just a little bit. We'll go ahead and talk about the last exam real quick. Where's my, there it is. Okay, so this is sort of the distribution for exam 3. lecture exam 3. So the median, which is sort of the relevant number, is about 72. Actually, this was before I entered a few more grades, so it ended up being about a 75 once I entered the last few grades. And so that's now posted on Blackboard. Okay, so you can take a look at what your grade is for that. As far as grading goes in this course, you should have read the syllabus hopefully in the beginning of the semester. Point totals changed a little bit, but the grading scheme is essentially the same. Labs and lab exams, you had 11 labs and then 3 lab exams. So 11 labs was 20 points each, right? And then the lab exams, another 120 points. That scales down to 40% of your grade, so we multiplied that point total, whatever you had, divided by 340, that's your lab grade. Similarly, lecture exams and CPS points, that was 60% of your grade. And so those for sure you should be able to get. If there's not a lab grade for you yet, it's only because you took the exam at the end of the week and your TA has not yet gotten to grading it. You guys? Okay. Okay, but anyway, by tomorrow, hopefully everybody will have their lab exam grades. And here's just an example of how to figure it out. Although I've done the calculation for you, but if you want to know where the math comes from, this is sort of what we've done. What you'll see on Blackboard is that I've already multiplied these numbers by 100 or whatever to get that percentage. So instead of 0.3, it'll be 30 points. So in any case, let's say someone got 255 points, you divide that by 340, multiply that 40%. That scales to 30 points, roughly, or exactly, to your lab grade or your contribution from your lab grade. And then your lecture, similarly, you got an average of an 82 on the CPS and lecture exams. And then you multiply that by 60. That's 49.2 points. You can add that all together. That would give you a grade of 79.2%, or a percentage of 79.2%, which would translate to a grade, which by Wednesday I'll have final brackets for those grades once all the lab grades are posted. Okay. So real quick comment about the final. We'll review things, content material on Wednesday. So come with questions if you have questions. But it's optional. So there's no penalty for taking it. But hopefully by Wednesday, I will give you an idea of what you need to do on the final in order to improve your grade and what's the maximum improvement you can have. Let's say you got 100 on the final. This is the maximum improvement you got. Let's be more realistic. Let's say you got a 90 on the final. What would your grade be? You can sort of do that math yourself, but I'll give you a sense of what that should be, or at least a formula to figure it out. And again, the final will replace your lowest lecture exam grade. In this class, there are minor few extra credit points in lab, but in general, there's no extra credit points. There's no the lecture exams and the labs are mostly done now. We just have to post a few more grades. And the only way to change your grade at this point would be by taking the final exam. And the final exam grade, or your final grade again, is that lab plus lecture. If it's a percentage times 100, otherwise it's going to be out of 100 points. Okay, I think one more thing here. Oh yeah, I cleaned up the grading book a little bit. So what you should see is your labs, your lab exams, and so forth, your total lab score, okay? Lab score calculated by 40%, your 3 lecture exams, your CPS points, that would come to an unscaled maximum of 330 points in this column. What it is out of 60 points, okay? And then a tentative final grade, okay? So final course letter grade without final exam, and more importantly, what your final percentage is right now without the final. And you can sort of see with those two numbers where you are right now and if you want to take the final exam.
You said you'll have the brackets at
Yeah, so as soon as all the TAs get me the lab exams and I can see that they're all there, I will finalize the brackets, okay, so that way you can know absolutely, if I don't take the final, this is what my grade will be. And then you can say, it's not going to change, okay, and after that. And that should be posted after Wednesday, okay, after the review, so at the latest. Oh, okay, and this is just straight out of the syllabus. And right now, this is sort of, to get that final grade, this is what I'm using. Obviously, I don't have what an A+ or A- is in here, but it extends to both sides of the range. Just to put it in perspective, the total accumulated points, the highest grade that someone had in the course so far, or in this semester, was a 97. So someone is in that range to the upper bracket as well. We've got people in all these, a nice distribution. It just happens. So this is sort of the pretty standardized ranges. Where things can change are what's exactly a B+ and what's exactly a B-, okay? So that's, or A-, B+, and so forth. But these boundaries are unlikely to change, okay? And this is exactly what's in your syllabus from the beginning of the semester. So that being said, this is what this previous letter grade is currently based on, okay? So if you have questions, bring them Wednesday. And there'll be additional information for you if you're taking the final then. Thank you very much.